In Unit 5.4, we're going to make definitions of medians, altitudes, and perpendicular bisectors. When you think about median, you think about middle. Remember when we talked about the measures of central tendency in the Algebra 1 textbook, and we talked about mean, median, and mode? And we said the median was the one in the middle when you align them from least to greatest, and if there's more than one in the middle, then the median is the average of those two. So when we think about median, we think about middle. Uh, when we think about altitude, we think about height, how tall something is, how high up something is. And a perpendicular bisector, we know what perpendicular means, intersect at 90. We know what bisector means, it makes two equal things, hits the midpoint. And so we've got some insight to these things already. Median of a triangle, though, is a little different concept than the median of a set of data. A median of a triangle is a segment from a vertex to the midpoint of the opposite side. To the midpoint of the opposite side. And here we go with that opposite stuff again. Pretty important to know what's opposite. So a segment from a vertex to the midpoint of the opposite side. This definition is supposed to tell us how to draw something from a vertex, B's a vertex, to the midpoint of the opposite side, a point that divides a segment into two equal segments. So BF would be a median because it is a segment from a vertex to the midpoint of the opposite side. So BF is a median to side AC. AE is a segment from vertex A to the midpoint of the opposite side, BC. So segment AE is a median drawn to side BC. C is a vertex. D is the midpoint of the opposite side, AB. So C is the midpoint drawn to, or segment CD, excuse me, is the median drawn to side AB. Notice that the medians of a triangle intersect at a point. That means that those are concurrent lines. We'll learn that later. Concurrent lines are lines drawn within a triangle or about a triangle or that intersect at a point. Lines that all intersect at a point are said to be concurrent at that point, and the medians of a triangle do that, and there's a certain relationship that happens within that triangle when the medians do intersect. Altitude. If we're thinking about an airplane, and this isn't going to be a very fancy looking airplane, so anyway, we've got an airplane zooming across here, and here's the ground down here. And we want to know, how high is that airplane off the ground? Well, would you measure like that to find its altitude? Or would you measure like that to find its altitude? Or would you measure like that to find its altitude? Well, none of those. If you wanted to know how high that airplane is off the ground, you would measure straight down so that it's 90 degrees, and that's the height or the altitude. The height of the airplane or the altitude of the airplane. So it's going to be a segment from a vertex perpendicular. A segment from a vertex perpendicular. Well, perpendicular to what? Well, let's look. Let's make a triangle. We've got to be careful on this definition. That's why I kind of left you hanging. Let's say we had a triangle that looked like this. Well, if we're going to go from a vertex, we could say, well, it's perpendicular to the opposite side. So can we finish our definition like that? Well, the answer is no, because what if we had a triangle that looked like this? And I wanted to know how tall that triangle is. Well, you can't draw from here perpendicular to the opposite side. You would have to draw the line that contains the opposite side. In other words, let's find out where ground level is, and we're going to draw from the vertex perpendicular to the line that contains the opposite side. How tall that triangle is not in the triangle, it's outside of the triangle. That altitude is not even within the triangle. So it's a segment from a vertex perpendicular to the line that contains the opposite side, because it may not can actually hit the opposite side, to the line that contains the opposite side. Now, what you're mentally thinking, remember, is from the vertex straight down, okay? Perpendicular, 90 degrees. A segment from a vertex perpendicular to the line that contains the opposite side. So let's look at BD. From point B, the line that contains the opposite side is there. The segment from that vertex perpendicular to that line containing the opposite side is BD. So segment BD is an altitude to side AC. Okay? Well, let's look at from point A. The line containing the side opposite point A is that line. If we go from point A perpendicular to the line containing that side, we get AF. So AF is the altitude drawn to side BC. If we're at point C, the side opposite point C is AB, so we would draw the line that contains side AB. From C perpendicular to the line containing side AB is CE, so CE is the altitude drawn to side AB. Notice that the altitudes were also concurrent at a point. Now, that was in an acute triangle. Notice in a right triangle, this is important. AB, if we want the altitude from A, then we would draw the line that contains the opposite side. The segment from A perpendicular to the line containing the opposite side is AB. AB is an altitude to BC. Now, the reason this gets to be important is, remember that the formula for every triangle is 1/2 base times height. If we let BC be the base, then what's the height? Well, the height is the altitude to that base BC. So this leg of that right triangle becomes the height that goes with this other leg of the right triangle. So this leg is the base or the bottom. When that leg is the base or the bottom, then this other leg is the height or the altitude. So in a right triangle, we can use the legs as the base and height to calculate the area with, because one leg is perpendicular to the other leg if it's a right triangle, C. Okay? BC BC, if we were at C, and we drew the line that contained the side opposite, C. From C, perpendicular to the line containing the opposite side would be BC. So leg BC is the altitude drawn to leg AB. Now, if we were going to draw the altitude from B, then we would have to draw the line containing the side opposite. The side opposite is the hypotenuse. From the vertex perpendicular to the line containing the opposite side would be BD. So BD is the altitude drawn to the hypotenuse AC. What if we had an obtuse triangle? If we had an obtuse triangle and we wanted to draw the altitude from A, we would have to draw the line containing the side opposite A. Now, before I do this again, let me talk about what the actual triangle is. Some people get kind of lost on, well, what's the triangle we're even talking about? Well, the triangle we're actually talking about is this triangle right here. Okay, now I could have made my coloring a little bit smaller. There's a possibility I can erase some of that and stay in the lines. Uh, if some of your little brothers and sisters are watching my coloring in kindergarten, they're going to be a little upset with me. Let me just color that in like this. So we're talking about this triangle. If we're talking about this triangle and we're looking at vertex A, then the side opposite A is BC, and we can't draw an altitude that's going to hit BC, so we would have to draw the line that contains the opposite side. Now, from that vertex, perpendicular to the line containing the opposite side is out here. So AD is an altitude to side CB, and it didn't even hit CB. It hit the line containing CB. See that? So that altitude was outside the triangle. So here in this acute triangle, we have a situation where an altitude is on the inside. Here in a right triangle, we have a situation where the altitude is aside. And here in an obtuse triangle, we have a situation where the altitude is on the outside of the triangle. Now, continuing here, if we wanted to draw the altitude from B, we would have to find the side opposite B. We would draw the line that contains the side opposite B, and we would have to go from B perpendicular to that line that contains the opposite side, and there we would have the altitude from B to AC. So BF is the altitude drawn from point B to side AF. And then if we wanted to draw the altitude from C, we would have to go to the line that contains the opposite side AB, and the line that contains that opposite side is actually inside this time. And so CE is the altitude drawn to side AB. So we've talked about medians, we've talked about altitudes, we've talked about medians, we've talked about altitudes. We have a little theorem 5.6 and 5.7, but it's instructing us here as a note to teach definitions 49 and 50 before we do these theorems. So we're going to skip theorem 5.6 for just a moment, theorem 5.7, and we're going to go to definitions 49 and 50, and then we're going to come back to those two theorems. The distance from a point to a line. As we think about those vertices and those altitudes, when this was a point like the airplane or a vertex, and we had a line containing the opposite side or ground level, then if we were going to draw a perpendicular, how many could you draw? Well, from that point to that line, only one perpendicular can be drawn. Now, we've learned that already. There's a theorem that we've already covered that says given a line and a point not on that line, exactly one parallel and one perpendicular can be drawn to the line. So there's only one perpendicular that can be drawn, but when we talk about the height or the altitude, we talk about straight down. Why? Well, straight down is the shortest distance. We're long, shorter, shorter, shorter. The closer that this angle gets to 90, the closer it gets to being the shortest distance. The shortest distance from a point to a line is the length of that perpendicular segment drawn from the point to the line. The distance from a point to a line I lost my stuff there, but that's okay. The distance from a point to a line is defined to be the length of the perpendicular segment drawn from the point to the line. The length of the perpendicular segment drawn from the point to the line. The distance from a point to a line is defined to be the length, how long that segment is, the length of the perpendicular segment drawn from the point to the line. The shortest distance is straight down, and it makes a 90-degree angle. That's what we see with our eyeballs. We got these fancy definitions, but then we look at it and say, oh, it's straight down. It hits at 90. Okay? We want to know the formal definitions, but we want to understand it in a simple way we can use it, right? Okay? The length of the perpendicular segment drawn from the point to the line. That's good to know. What does that mean? Straight down. It hits at 90 degrees. There you got it. Okay? The perpendicular bisector of a segment. Now, perpendicular lines are two lines that intersect to form equal, adjacent, 90-degree angles. The bisector of a segment is a line, segment, ray, or plane that intersects a segment at its midpoint. That's the formal definition, but what we're more interested in is what you get out of it. And what you get out of it, besides it hits it at its midpoint, is that you get two equal segments. The formal definition, though, the perpendicular bisector of a segment is a line, segment, ray, or plane that intersects a segment at its midpoint and forms equal adjacent 90-degree angles. So it hits at, we're making an informal definition, hits at 90 degrees and divides it into two equal segments. I want you to memorize it with the what you get out of it, because that's how you're going to use it in a proof anyway, and that's how you're going to use it. Again, the formal definition is a line, segment, ray, or plane that intersects a segment at its midpoint and hits at 90 degrees. So it's a perpendicular and a bisector. Well, what do we get out of a bisector? Two equal segments out of a bisector of a segment. So what we get out of it is 90-degree angles and equal segments. It's an object that hits a segment at its midpoint and makes a 90-degree angle. Okay? So, given that PM bisects is a perpendicular bisector of AB, given that PM is a perpendicular bisector of AB, what can we conclude? We can conclude that AMP is equal to PMB. We can conclude that they're equal. Angle AMP is equal to angle BMP, and that they're both equal to 90. They're perpendicular. They form equal adjacent 90-degree angles. Equal adjacent 90-degree angles. And it bisected it, therefore it divided it into two equal segments. Therefore, we can conclude that AM is equal to BM. And the reason we can make this conclusion or this conclusion given this statement would be definition of, remember we have the word in what you get out of it, definition of a perpendicular bisector of a segment. Definition of the perpendicular bisector, and the only thing we would have the perpendicular bisector of is a segment. Okay? Definition of perpendicular bisector. So we got the definition of the distance from a point to a line or plane is defined to be the length of the perpendicular segment drawn from the point to the line or plane. And then we've got the definition of the perpendicular bisector of a segment. We said it is an object that intersects a segment at its midpoint and forms equal adjacent 90-degree angles. In other words, it hits at 90 and divides it into two equal segments. We can conclude that the angles are equal, or that either of those is 90, or that the two segments are equal using the reason definition of a perpendicular bisector if we was going to do a proof. If we were going to do a proof. So let's back up and pick up those two theorems, Theorem 5.6 and Theorem 5.7. Theorem 5.7 says if a point lies on the perpendicular bisector of a segment, then we can conclude that it is equidistant from the endpoints of the segment. Now, why can you conclude that? Let's just look at this. If this point lies on the perpendicular bisector of a segment, why could we conclude that this has to be equal to that? Well, you remember the isosceles triangle theorem? In the isosceles triangle theorem, we said there's four things marked. The two equal sides, the vertex angles being equal, the 90-degree angles, and the base being bisected. See the two blue things and the two black things? We said if any two of those are true, you can automatically conclude that the other two are true by the isosceles triangle theorem. So the isosceles triangle theorem allows us to reach the conclusion that if a point lies on the perpendicular bisector of a segment, then that point must be equidistant from the endpoints of the segment. So it's equidistant from point A and point B. In other words, PA is equal to PB, meaning what we have here is an isosceles triangle. Okay? One more run through. PM is a perpendicular bisector of AB. The theorem says if a point lies on that, it's equidistant from the endpoints. Notice no matter where it lies on that, it's equidistant from the endpoints. We're going to get an isosceles triangle no matter where we put that point. See, we could go way up here. If that lies on the perpendicular bisector, then it'd be an isosceles triangle, see? All right. Theorem 5.7. If a point lies on the bisector of an angle, if a point lies on the bisector of an angle, then it will be equidistant from the sides of the angle. If a point lies on the bisector of an angle, let's look at that. We've got angle CAD. We have that ray AB bisects angle CAD. This theorem says if a point lies on that, then it's equidistant from the sides. Now, remember the distance from a point to a line is the length of the perpendicular segment drawn from the point to the line. So any point that lies on the bisector of that angle would be equidistant from the sides, and distance meaning it hits it at 90 degrees of that angle. Okay? So, B is equidistant from ray AC and ray AD, meaning that the distance that B is from side AC, which is the length of segment BC, is equal to the distance that it is from side AD, and the distance it is from AD is the length of the perpendicular segment from B to AD, which is segment BD. So if a point lies on the bisector of an angle, then it's equidistant from the sides of the angle, the distance being the length of the perpendicular segment from the point to the line, as we define the distance from a point to a line. Any questions on that? Okay. So we talked about, as we review here, medians. A median is a segment from a vertex to the midpoint of the opposite side. An altitude is a segment from a vertex perpendicular to the line that contains an opposite side. An altitude could be inside the triangle, one of the legs of a right triangle, or outside of the triangle if it is an obtuse triangle. A perpendicular bisector of a segment is an object that intersects a segment at its midpoint and forms equal adjacent 90-degree angles. So it hits at 90 and divides it into two equal segments. We went back to theorem 5.6. If a point lies on the perpendicular bisector of a segment, then it must be equidistant from the endpoints of the segment. Theorem 5.7, if a point lies on the bisector of an angle, then it is equidistant from the sides of the angle. we defined, I don't know if I said it or not, the distance from a point to a line is the length of the perpendicular segment drawn from the point to the line. That's definition 49. Okay? Hard to believe here, just a milestone, that we've made 50 definitions. There's right about 100 definitions. I think there's 90 something, maybe 99 definitions in this book. A lot. Uh, that's a lot of stuff to know. If you are somewhat lost in geometry and your teacher's saying things like the isosceles triangle theorem, the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint, it's going to sound almost like your teacher is speaking a foreign language if you don't know those definitions. Because when those terms come across your brain, if your brain doesn't automatically throw out a definition in a split second and give you a picture of what that is, then you have no clue what your teacher's talking about. So it's very important that you're up to date on your definitions, postulates, and theorems, so when your teacher's speaking this geometry language, you know what she's talking about, or you know what he's talking about. Okay? Let's look at daily work 5.4. It says name a median. Name a median. A median is a segment from a vertex to something. Well, there's not one there. A segment from a vertex to the midpoint. That's not a midpoint. A segment from a vertex. I'm messing up on purpose, obviously, you know. A segment from a vertex. Are we seeing why we need the definitions? A median is a segment from a vertex to the midpoint of the opposite side. IX is a median. An altitude. An altitude, we got to say the definition. It's a segment from a vertex perpendicular. Perpendicular. A segment from a vertex perpendicular to the line that contains the opposite side. EU or UE is an altitude drawn from U to side AI. An altitude, UE. So we're having to use our definitions to be able to name these, okay? And you can continue that. Since Z lies on the what? Well, what does Z lie on? This thing, ZF. Well, Z lies on ZF. Well, what is ZF? ZF is a perpendicular bisector of BG. So Z lies on the perpendicular bisector of segment BG. Therefore, we can conclude what? Well, you got to go back to the theorem. If a point lies on a point that lies on the perpendicular bisector of a segment is equidistant from, and then you'll be able to answer that, right? F lies on what? Point F, number 6, lies on ray XF. Well, what is ray XF? Well, this little angle is equal to this little angle. Therefore, it must be the bisector of that angle. So point F lies on the bisector of angle PXE. Therefore, you can reach what conclusion? Okay? BE. BE. How long is BE? Well, we've got that this angle is equal to this angle. And we've got that this is 90. And that's 2 out of the 4 things associated with an isosceles triangle and the isosceles triangle theorem. We're going to look at this triangle, triangle ABE. Since 2 of the 4 things that could be true in an isosceles triangle are true, then we could conclude that the other 2 are true. In other words, this really is an isosceles triangle. So if that's 10, that's 10. And this thing, this vertex angle bisector, is perpendicular to the base at its midpoint, so Phi is equal to 6. So we could say that BE is equal to 10 because of the isosceles triangle theorem. And then we could just go crazy with a lot more geometry stuff. We've got all of these theorems we just learned on top of the isosceles triangle theorem, on top of a lot of other theorems. Let's just look at this little situation. You see this situation? We've got the bisector of angle CAE. What you've got to start being able to do is looking at a picture and all these little theorems jump out in your head. You've learned them so well that you just see it. Ah, that's that little situation. We've got an angle bisector. D is the point that lies on an angle bisector. A point that lies on the bisector of an angle is, remember that theorem? And the conclusion, what do you know about DE? And what did that theorem that we just almost quote say? So what would our reason be? You got to go back and look up that theorem. If a point that lies on the bisector of an angle is, that's a pretty long reason. You just abbreviate that all you can, okay? Draw and label. These can get a bit tricky. I'm going to freehand it. If we wanted an acute triangle ABC with AB at 3 centimeters, BC at 5 centimeters, and draw the altitudes, here's what you'd have to do. I'd start off myself with a ruler and I would measure 4 centimeters. Now I'm just making this bigger just so you can see it. 4 centimeters is the width of 4 thumbnails. That's not very wide. So I'm going to start with AC at 4 centimeters. And then I would open up my compass, right, to 3 centimeters. And I would put the pointy part on A. And I would make an arc across 3 centimeters. And then I would open up my compass to 3.5 centimeters. And I would put my pointy part on C. And I would open it up and I would make an arc. And that arc would be 3.5 centimeters from there. And I would find the point where those two met, and then I would connect. And I would have AC at 4 centimeters. I would have AB at 3 centimeters. and I would have BC at 3.5 centimeters. Okay? If I was going to draw the altitude from B to AC, what I would do personally is I would take my protractor and I would find the little hole and I would find the 90 mark and I would slide it until it lined up. If it doesn't quite line up, I would slide it a little bit more until it lined up. If it's not tall enough to see, then set you a ruler right there on that 90 until you can see where it slides up against that. And then I would draw the altitude because the altitude is from the vertex perpendicular to the line that contains the opposite side. So you're going to slide that across until it's 90. Okay? And we can look at the other draw and label the examples accurately. You can look at the odd ones. Those would be displayed for you, precisely drawn in the uh, odd answers. I do need to tell you, though, that when these pages were printed from the original, they may have been enlarged or reduced to fit the page better, so they may not actually be the right length exactly anymore. So again, you probably need to refer to your instructor for perfection and exactness. Okay. All right. And then at the end of that, use diagrams and a protractor to reach conclusions. And again, the conclusion would be the next lesson. There's lots of reaching conclusions here. And that would bring us to 5-5 concurrent lines. And the conclusions at the end of daily work 5-4 would be the lessons here in Unit 5-5.